M. Here also strength of north pole is m and strength of south pole is also m. Root over r square plus l square whole square, because this is the distance between north pole and P point. Now B2 is the magnetic field at point P due to south pole, and the magnitude of B2 equals to mu naught by 4 pi m by root over r square plus l square whole square. Just look at here, this is the direction of B2 along this side, right? So here we can, that means these two vectors are, B1 is along this side and B2 is along this side. If this angle is theta, then this angle is also theta, because these two angles are alternative angle. That means we can resolve B2 vector, then we will get one component along this side which is B2 cos theta and another component along this side which is B2 sin theta. If this angle is theta, then this one is also theta. These two angles are corresponding angle. That means we will get one component along this side which is B1 sin theta and the another component along this side which is B1 cos theta. So just look at here, the magnitude of B1 equals to magnitude of B2. That means B1 sin theta cancel by B2 sin theta. So the net magnetic field at point P due to this bar magnet is the addition of this two component. So mod of B1 equals to mod of B equals to B. So B1 sin theta equals to B2 sin theta. They are cancelled to each other, right? Net magnetic field at point B equals to B1 cos theta plus B2 cos theta. So 2B1 cos theta. Now 2 into mu naught, this is the magnitude of B1, mu naught by 4 pi m r square plus l square into l by root over. This is the value of cos theta. Just look at here. If we take this right angle triangle, then this one is base and this one is hypotenuse, right? So L base by hypotenuse equals to cos theta. So this is the value of cos theta. Then after solving this, we will get B equals to mu naught by 4 pi. This one is m. M indicate magnetic dipole moment of this bar magnet, which is m into 2L. So m, capital M, by r square plus l square whole to the power 3 by 2. In vector form, B vector equals to minus mu naught 4 pi m vector r square plus l square whole to the power 3 by 2. This negative sign arises here because here B vector and m vector both are in opposite direction. This is the direction of m vector and this is the direction of B vector. So both are in opposite direction. That's why this negative sign arises here. If we assume that r greater than L, that means we can consider L is 0 compared to R. So that means B equals to mu naught 4 pi m r to the power cube. So this is the value of magnetic field if we assume that R greater than L. Next topic is torque on a magnetic dipole, that means bar magnet in a uniform magnetic field. So here I am taking a bar magnet and magnetic moment of this bar magnet is along this side. This is south pole and this is north pole, and this magnetic moment makes theta angle with this magnetic field. This is the direction of magnetic field. Okay, so angle between magnetic moment and bar magnetic field is theta. So you can see here, if the magnetic strength of north pole is m, then the force on north pole is along this side which is mb, and if the magnetic strength of south pole is also m, then this is the force on south pole which is also mb, right? So these two forces, just look at here, these two forces are similar but act in opposite direction and the line of action are parallel to each other. That means these two forces generate couple in this bar magnet, right? What is the value of couple? So first we have to find out perpendicular distance between these two line of action. So BC represent perpendicular distance between these two line of action. So what is the value of BC? BC equals to AB sin theta, right? Because if we take ABC right angle triangle, then BC by AC equals to sin theta. So BC equals to 2L into sin theta, because AB equals to 2L, which is the length of this bar magnet. So torque equals to either force into perpendicular distance between line of actions. So MB into BC. So MB into 2L sin theta. So here M into 2L into B sin theta. That means M into 2L represent M capital M, which is magnetic dipole moment of this bar magnet. So capital M into B into sin theta. So this is the value of torque if we placed a bar magnet in external magnetic field, then that amount of torque act on this bar magnet. Okay, so tau equals to mb sin theta. So if we represent in vector form, then tau equals to m cross b. Okay, not b cross m, m cross b. When theta equals to 90 degree, then tau is maximum, which is mb. When theta equals to 0 degree, then tau is minimum, which is 0. Last topic is bar magnet as an equivalent to current carrying solenoid. So to prove mathematically the equivalence between a bar magnet and current carrying solenoid, we shall calculate the axial field of a finite solenoid and shall demonstrate that at large distances this axial field resembles that of a bar magnet. That means here we have to take a where we have to take a solenoid. Just look at here, this is a solenoid. And the length of this solenoid is 2L, and this is the axial line of this solenoid, right? And we have to take a point P on this axial line, and suppose this P point placed at distance from the center of this solenoid. Okay, now the radius of this cross sectional area of this solenoid is A. Okay, so here large number of turns are present. So here I am assuming that n number of turns per unit length. So this solenoid hold n number of turns per unit length. So here you can see here I am taking a dx elementary cross section, dx elementary circular loop, or we can say cross section, which is placed x distance from the center of this solenoid. So this loop is looking like this. This is our loop, and the width of this loop is dx. So that means total number of turns in ds width is n into dx, right? Because n is the total number of turns per unit length. That means dx length contain n into dx number of turns. So now consider a circular element of thickness ds, this is of the solenoid at a distance x from its center. It consists n into dx number of turns. Let I be the current in the solenoid. That means each and every turn, I is the current passing through each and every turn. Okay, so if dB is the magnetic field at point P due to this circular loop, then dB equals to what? We already find out for a current carrying circular loop, magnetic field at a axial point, which is equals to mu naught by 4 pi equals to 2 pi n I square, where n is the total number of turns, I is the current passing through each turn, A is the radius of this circular loop, and x is the distance between center of this circle and the P point where magnetic field is required. So here I am writing this. So here I am finding magnetic field at point P due to this current carrying loop. Here total number of turns is n dx. So just this is the equivalent to this equation. So mu naught by 4 pi, just look at here, 2 pi, n is the total number of turns. Here total number of turns is n into dx, into I is the current and A is the cross sectional area. So A is the radius of this loop, this is A, right? By A square plus x square. What is x? X is the distance between this point and center. So we have to take this distance, right? So what about this distance? This distance is r minus x, right? So a square plus r minus x whole square whole to the power 3 by 2. So now the magnitude of total field will be obtained by integrating between the limits x equals to minus L to x equals to plus L. So thus B equals to integration minus L to plus L dB mu naught by 4 pi, all are the constant, only x will be vary, right? At here x will be vary. So 2 pi n I a square all coming out from this function, so minus L to plus L dx by this. So here we assume that r greater than a and r greater than 2l. That means this term will be r cube, right? Because compared a and x become to 0 compared to r. So that means b of mu naught 2 pi n I square by 4 pi integration minus L to plus L dx by r cube. So r is also constant because r cannot change, only x will vary, right? So r also coming out from this function. So if we integrate this, then we will get 2l. So mu naught 2ln into I pi r square into 2 by 4 pi r cube. So what is this? This is the magnetic. What is this? This is the total number of turns, right? So here I am assuming that total number of turns is n. This is the total number of turns of this solenoid, because n is the number of turns per unit length and the solenoid length of this solenoid is 2l. So this is the total number of turns of this solenoid, which is, here I am assuming, capital N. And this is I, and pi r square. What is pi r square? Pi r square is the cross sectional area of this solenoid into 2 by 4 pi r cube. So B equals to mu naught 2m, because we know magnetic moment of current carrying loop equals to number of turns into current into area of that current carrying loop, right? So 2 into m by r cube. So this is also